All right, welcome everybody to the next New York Combinatorics seminar. Today we've got Robert Donley who's going to talk to us about anti-magic squares. Take it away.
Great. So thanks to Deepak for the invitation. Thanks everyone for showing up. And it's great that this year I have a combinatorics talk to bring. So great to be back. All right, so anti-magic squares and conjoined compositions. And I hope this is, of course.
Oh wait, yeah. I have to. Yeah, this happens every time. My mouse over there. Click once.
Okay, all right, great. So for overview, 3 parts. The first part, I'm going to tell a story about binomial coefficients. Like binomial syndrome, because we're doing combinatorics, there's the Catalan disease, really binomial coefficients that have their own thing also. So I want to tell a story about binomial coefficients, and then that story I want to ask, is there anything that I could just plug right into that story and get the same, new story, just a little bit of an upgrade? And that's going to be anti-magic squares and conjoined compositions, and then the way out is just talking about counting formulas for these things. I'll note where this is coming from. Okay, so trying to anti-magic squares kind of came onto my radar like a while ago, 2022. It's like magic squares are probably too difficult for undergraduates. So the thing is, what's a lot like magic squares but not quite so difficult, and that's anti-magic squares. So I launched a project then, 2022, 2024, and we got some results, but I felt like it was still not ready for publishing. So 2026, I kind of decided to go back to basics with it, and then that's what this talk's going to be about. And this is definitely ready to launch. I'll also know this has been back in my mind, so gratitude to CUNY Fellowship Leave, and that happened at Institute for Advanced Study last year, so acknowledgements. All right, so what are we doing here? Oh, one other thing. Get up. All right. So someone asked, where can I find this? So the official paper is not written yet. That'll probably be the summer. One thing I've been doing for like the last 4 years nonstop with finally a break. I had to skip an issue for the last one, but this issue I'm back in. So Girls Angle, it's sort of it says K through 12, but it feels more like an undergraduate magazine, all kinds of subjects. The current issue is part 3 of a cycle on anti-magic squares, which is a subject matter for this talk, but for undergrads in K through 12, in the Harvard area, I guess. So this is the talk. There will be 4 parts, so you're also going to get a sneak preview for part 4. All right. Okay, so where this begins, binomial coefficients. Okay, so I want to start with binomial coefficients in this form, where I have 2 parts in the upper index. I write it out, and then what I want to do is we're going to treat t eventually as a variable, so I could wash out the t factorial from the bottom, and then I'm going to be left with this expression over on the right. What are we doing here? With this represented like this, it's the number of ways to put t-balls into n+1 boxes, and then the official combinatorial gadget for that is weak compositions. So you should think like a partition. We're allowed to have zeros, and the order matters. And let's see. So for notation, instead of using tuples, I want to use boxes like we do for Young diagrams. This won't be nearly as interesting as Young diagrams, but it is convenient for where things go. Okay, so we should make sure that proofreading held up 22035 does add up to 12. All right. Now, we have a polynomial. This polynomial is completely determined by the fact that we know where the zeros are. It factors completely, and that at 0 we get value 1. Polynomials, so I'm doing college algebra every semester. If you give me a polynomial, I'm going to take a look at its graph and see what's up. And of course, if you take a look at the first couple, well, these are obviously even and odd, but just not in the right place. So if the y-axis is off to the right, then I'm getting even or odd if I'm willing to do a shift. And that's going to be kind of a feature of where I want to go with this, like what things can you do with undergrads. Undergrads should know how to do operations on functions. Now, another interesting thing about polynomials, if you have counting functions, okay, if we're in combinatorics, we should check for reciprocity. So the idea is going to be if you have a nice counting function, if it's polynomial, I should take the variable and replace it with this negative, and I can hope that something interesting is going to come out with that replacement. And I'm not going to say a lot about where that officially lives, which is in the area of polytopes and Ehrhart theory. Keep it to the undergrad version. But for a binomial coefficient, if you do the switch, what happens? What do? You put in negative t. I could use the polynomial expression, wash out all the negative signs, and then that's going to reverse where your top index is. And so then when you reorganize, you're going to get this shift in the bottom. And so, and I'll also, of course, I'm reading books on this. This morning, I finally realized, maybe I should go look to Stanley's paper on combinatorial reciprocity, finally. And he attributes this to Riordan. Riordan kind of just does this and says nothing more about it. And that's Stanley's note on this. Okay. All right, so what's the interpretation here? Combinatorial reciprocity. What combinatorial reciprocity does for polytopes, you have say a lattice polytope, you dilate it. If you do counting, the count with the dilation is going to fit to a polynomial if things are nice. And then the idea is when you do the shift with the negative t, that's going to go from counting the lattice points in the full polytope to the counting function for the points of the interior. So if I think of that with weak compositions, going to the interior means you're not allowed to use any zeros. So we're going to switch from counting weak compositions where I allowed zeros to ones without zeros. And then a trick I'm going to use over and over again in this talk is, well, how do you do that count? You're going to have a composition. I don't want zeros, so I just pre-assign a 1 to each box, which is going to cut the number of balls you can put in there by an n+1. And so that's why you get the shift. And then the sign is just in there for reasons. I guess just because that's the way it is.
Counting the interior points in the polytope.
I think you went on the boundary also.
Oh, you're saying.
Yeah. So the shift, the t to negative t takes you from the full to the interior.
Oh.
Yeah. All right. To be clear on what this shift is doing, because it's not negative t to t, it's negative t to a t minus a number. So that's going to be your even and odd after you do a shift. And so there's going to be a fixed point in here. And to check on that, you could just take your negative t, your t minus n minus 1, and just look for the midpoint. And then that's going to be where I want to center things when we reconstruct the polynomials with the symmetries. All right, so if we check some of these, just to check that this actually works, it's undergrads. It's the kind of thing maybe you don't do in a paper for a good journal, but for undergrads, seeing is believing. We notice for the even ones, if we rewrite according to whether you're even or odd, then we see that the evens are going to give us even polynomials, the odds are giving us odd polynomials, and for the odd polynomials, so it's enough to see if we do the odds, kind of a nice representation of this with the even and odd, and also you'll notice there's this progression of differences of two squares. That'll be a feature, and not that I'll explain it, but I'll do a calculation later on where it's just kind of, if you don't see it, it's clear that we have to have something like that. All right, so that's talking about the binomial coefficients of polynomial. Of course, binomial coefficients go with Pascal's triangle. I want to think about Pascal's triangle a little bit differently than I normally would. Normally, we think binomial theorem. Another way to hit Pascal's triangle is instead of considering the rows, to consider the diagonals. So that's going to bring us to binomial series, which are going to be a featured player in this. And what we're doing is with the binomial series, so you'll see the binomial coefficients in the form that I started with. This is going to give us each diagonal is going to give you the diagonal coefficients for these as series. All right, what's going on here? Okay, if I start with a geometric series, if I take, say, generating function for any sequence, if I multiply by a 1 over 1 minus x, when we do that to calculate the new coefficients, that's a discrete convolution. But since I'm using the geometric series, those coefficients are all 1. So all we're doing is taking a partial sum sequence. So that's the results of partial sum sequence. If I take n plus 1 of them, then that's just n plus 1 partial sum operations. If I let f of x be 1, which is what we want for Pascal's triangle, then that's how another way to construct Pascal's triangle. Instead of doing the 2 above, now I just run down a diagonal and take partial sums of the 1 above. Right. So you also note, kind of nice, my second talk this semester where I get to use Excel. So I did a few years as an actuary and never used Excel ever again until I kind of got back into the research thing. So like I really do like look for opportunities to break out the Excel. All right, so how do I want to organize things for Pascal's triangle? This is obviously not a triangle, it's a rectangle. In the middle, I want to put the apex, so that's a 1 followed by a bunch of zeros. That's f of x equal to 1. And then I'm going to take partial sums if I want to construct to the right. So for instance, if I take the 10, what do? We just take a look to the left and then sum up everything in the column. And then you can just real easy to iterate that in Excel. If I want to go to the left, well, same idea. I just have to flip my 1 over 1 minus x. That's just multiplying by 1 minus x. So I'll get Pascal's triangle as you'd expect in triangle form, but with the alternating sum. All right, and it'll be interesting to have both sides here. Note we're doing things backwards, so I got to work to get Pascal's identity. Well, how would I get that? I just take a look at the 6 above the 10, and then I realize, I can just evacuate the partial sum there, and then we get our 3-term recurrence. All right, so that's part of the syndrome. We've got explicit polynomials with even and odd. We've got hockey stick rule, partial sums. We got Pascal's identity. And then the last one's a little bit weird. Okay. Another thing we do with binomial coefficients is Vandermonde convolution, or Vandermonde convolution, if we're going to be up to date. So this is going to be a discrete convolution with binomial coefficients. Several proofs of this. The natural one would be is that I take a set. I want to draw k elements from that set. What I can do is condition on where those k elements come from if we fix a disjoint unit of that set. So, and that's exactly what that says. We condition on the amount we draw, say, from x. There'll be k minus I from y, and then there'll be independent choices, so you just multiply and then you just sum over. And that's Vandermonde convolution. Another way to do this is also, you could go right to just doing it purely functionally, where you're just picking off the coefficients in 1 plus x to the n plus n, where you just arrange your, how many ever you want to put in each factor. All right. Now, Vandermonde convolution, though, you should not think of as just being a single identity. It's actually a family where you're allowed to vary things. I'm allowed to vary the number of elements that I draw, and I'm also allowed to vary, say, if I have a fixed set, the m and the n aren't important. The only thing that's important there is the m plus n. So we can increment up and increment down, and that's going to have an interesting effect when I go back to the rectangular expression. To explain why the weird rule I'm going to have in a second happens, a way to think of this is if you have any two power series, we can put or the set of power series, I could put a bilinear form on that. All I do is multiply them together and pick off the Cave coefficient. If we take a look at what's happening there explicitly, okay, well, taking the K coefficient is just going to be our discrete convolution. Discrete convolution, if you look at this, it's like having two vectors. I'm going to reverse one, and then I'm going to dot product. So this reversing and dot product is what's going to happen on the next slide. Now, this thing's invariant under multiplication, meaning in this bilinear form, I can move any function that I'm multiplying by to the other side, gives the same answer, because there's really not a whole lot going on in computing. If I use 1 over 1 minus x, that's the function that defines my table. So that's not going to like mix things up. It's just going to push one column out, one column to the other side. And so the gray is not coming in so great, but that's fine. So what Vandermonde convolution looks like in terms of the table is what you do. You pick your favorite rectangle from the table. It's got to be attached to the top. And then what I'm going to do is I'm going to take the outer columns, flip one, and dot product. And with the last part of that, what that says is if I telescope in or telescope out, that dot product is not going to change. And then that's Vandermonde convolution by a table.
Sorry, can you see what the columns are again?
So remember, that's just binomial series. So like this one is the series for 1. This one is 1 over 1 minus x. And you read down in increasing powers of x.
Those are the coefficients.
Yeah, only the coefficients. Right, so I guess, sorry, going through this kind of quick. And so that's Vandermonde convolution is the I guess the third or fourth thing I want in my binomial syndrome. So this is going to be something that really doesn't depend on binomial coefficients. It's just building a table with a uniform rule. You get this for free. All right. So that's the story for binomial coefficients. So now I'm just going to introduce the magic square overview, and then we kind of just push all this through the same thing I just did. All right, so now, like I said, semi-magic squares kind of too difficult for undergrad project, but that's where we get all our motivation. So definition, semi-magic squares, not your traditional magic square. We want to loosen a lot of the conditions up. We can have non-negative integers for entries. We can reuse the entries. And then the condition we want is that the sums along any row or column are equal. And then that's what we call the line sum. Note here, no diagonals either. For examples, okay, so here are some examples of semi-magic squares. And you'll note, make an effort to box things. You could think of this as being, we're dot producting with special matrices where, like, for instance, this one could be a shorthand for dot producting with the matrix, which has zeros in the first and third rows, but ones in the middle. That's going to be useful for something later on. All right, semi-magic squares, I'll talk about how you build these up in a second, but one thing you notice, every Latin square is going to be a semi-magic square. So that's a thing that is part of the theory too. Okay, magic squares, just big overview. Probably your first big, so of course, semi-magic squares, I'm not doing the magic square rundown because that goes back, could go back thousands of years, maybe, at least 500 for sure. For semi-magic squares, McMahon gives a formula in 1916 for size 3. The way I get into my interest in this comes from particle physics, where for some reason, right after, like you're talking the late 20s, right after spin and angular momentum are kind of booted up as part of Schrodinger's equation. When you do coupling, semi-magic squares are what you need to index everything. And so that becomes a thing that's very interesting to physicists. And unfortunately, a lot of that theory is bottled up in the physics literature. So it's not like freely available to mathematicians in a sense. You got to kind of learn some of the language. Probably the next one after that, the Birkhoff-von Neumann theorem. I'll talk a little bit about that. That has to do with the Birkhoff polytope. And then probably the result that has the most to do with kind of what this talks about is the Anand-Damir-Gupta conjecture from the 60s, which is an early landmark result by Stanley. So he extended and proved that. And the theory there is like if you got the Stanley library, that's the green book. That's the commutative algebra book. So there's a lot of ring theory and other things that go into that. That's definitely too much for undergrads. Moving forward, at least with the counting formulas, I think to date, the record is Beck and Pixton giving the polynomial explicitly for semi-magic squares of size 9. Oh, I should note, the Anand-Demir Gupta conjecture is about the generating function for the counting function for semi-magic squares. And so and it's not like a closed form. It's just really it's so difficult that like really the conjecture is just about the shape of what the generating function looks like. Yeah.
And the when you're counting, you like fix an alphabet or something?
Picking the line sum.
Oh, fix the line sum.
Right. We count by line sum. So I'll talk a little bit about that coming up. All right. And so like I said, state of the art 2003 is size explicit polynomial for size 9. And then the explicit generating function 2009, although that's not in the same, if I remember right, it's not quite the same form as Stanley's. Like I think theirs is multivariable, which makes it different. All right. So what do we have? Okay, so let me tell you the story of Birkhoff von Neumann. So for semi-magic squares, how do you make a semi-magic square? Well, if I have line sum 0, that's the 0 matrix. That's pretty easy to count. Otherwise, okay, we go up. Line sum 1. If you have a 1 in each row and column, then we've got permutation matrices. There is also important. Arrange these like this for the 3x3s. You'll notice the rotations and the reflections kind of fit together perfectly as puzzle pieces if you add them together. And then it'll turn out if I have permutation matrices, any linear combination of permutation matrices, and here when we say linear combination, really we're just doing sums because I'm not allowed to use negative numbers or things. If you use L permutation matrices, then you get another semi-magic square with line sum L. All right, so that sounds great. That's a nice uniform way to generate a lot of these things. And then Birkhoff von Neumann, a corollary to that says that every semi-magic square with line sum L can be written as a sum of L permutation matrices. So that's a complete statement. We know how to at least characterize semi-magic squares in terms of permutation matrices. The problem is, though, is we're not really doing linear algebra here. Like, what do we have? We're going to have a lot of relations, and they're not going to be great relations because we're working over natural numbers. That's what makes a theory so hard. Stall. Or it's hanging. I can't tell.
Let's click once and see if it fits. Okay.
Okay, great.
All right.
All right. So what I can do, even though we're not doing linear algebra, I can still actually let's take a look at the 3x3 case because that's going to point the way out of the difficulties. So if I take the 3x3 case, I take a linear combination, I solve. I notice there's only going to be one relation, and that relation is kind of like I noted. The sum of the rotations equals the sum of the reflections gives us the matrix of all ones. And then there's no other relations. The only way I can have a relation, I have to go through this matrix of all ones. So that means if I have a semi-magic square with a 0 entry, I can't use this relation at all, and that means the representation is unique. Otherwise, I'm going to be able to shift from, if you have the matrix of ones as a possible summand, then you're allowed to shift terms from one side to the other. You got n plus ways to do that if you have the smallest entry equal to n. And so that at least, while we don't have control, we don't have linear independence, we have a great deal of control of how to count these things if we want by line sum. All right. So I want to reconfigure things. So of course, with that, I can now get, for size 3 at least, I can get rid of the squares. I just want to change things over to tuples, and then it'll be convenient to take the tuples and like stack them. So the idea will be then is that relation for the J matrix, the 3 rotations equal to 3 reflections, I could think of that as being, if I do a tuple, it's moving 3 1s here to 3 1s over there. The semi-magic square won't change at all. You're just taking 1 1 1 and rewriting it as another 1 1 1. And so if I want to count, I just have to account for this shift in the representation. All right. And I'll note if I want to have a unique representations tuples, then all I got to do is shift everything up until I can't shift anymore, which means I have to have a 0 in the second row. And then that's where we can do Stanley's exercise 53. So spoiler alert, if you haven't read, of course, it's combinatorics seminar, so we've all read EC1 cover to cover, right? So what happens is when you go size 4 and beyond, size 4 is already kind of going into the weeds with difficulties and a large number of relations. So what's the solution if you want to do an undergrad project? If I take a look at size 3, chapter 4, problem 53 of EC1, Stanley has a question. He doesn't pose it like this. I'll give you the proper way it's posed on the next slide. But the idea is to switch up your permutation matrices with the things you were dot producting with. So these are like the things you dot product to get the line sums. Okay, that's if you dot product a matrix with this, you're just adding up the entries in that row. So we're gonna consider squares that are linear combinations of these things now. So that's what you call an anti-magic square. Now, like I said, I'm starting from the basis and telling you what it is. A more natural way to describe this is, you note, take a look at the things in the boxes. What we're doing here is dotting with permutation matrices. An anti-magic square is going to be a matrix such that if you dot with any permutation matrix, we get the same answer. So it's sort of kind of like a backwards semi-magic square. Really, it's the dual because you're using the other vectors. All right, notice, okay, you sit down, do the exercise of trying to write out how you represent this. The top one, I've got the 0 on the other side, and then I can bring a 1 1 1 over until or actually it's going to be the 1 1 1 pushes over there, 1 1 1 pushes over there, and then the then I can't push anymore because of the 0. Let's see, the smallest entry here is a 2. So I'm getting 3 ways to write this. All right. So that's an example of this. Okay, and so same idea. Now I could generalize this to any 2n tuple. Like so that'll be for size 2 by n or size n by n anti-magic squares. I could represent as 2n tuples now because we got nr's, nc's, and we can add them together. And then I'll stack that, and then the relation is still going to be the sum of the columns equals the sum of the rows. They're still going to add to the J matrix, and if you check it, they're going to be linearly independent. Or no, absolutely not linearly independent. They're going to be spanning. All right, and then and also spanning, but we only have one relation.
What's spanning?
I can get every anti-magic square can be written as a linear combination of the R's and the C matrices.
I thought that's how you define them.
Well, that's how I define them,
Oh, okay.
but that's part of the exercise. Is Stanley starts with the dot product with the permutation matrix, and then part 2 is show that every one of those can be written in terms of, you know, the R's and C's. Okay. Now, also spoiler alert, more. So part of the exercise is the counting function for this. So like I said, if I have this shift thing, I can get a preferred representative by just shifting everything to the top row, which means I have to have a 0 in the bottom row. So we've got definitions. The row is going to be the counting function for a fixed, if it was a semi-magic square, it'd be a line sum. We call it the index for anti-magic squares. When I get to conjoined compositions, I'm just going to call it a weight because this should be called a weight. So we have this formula here, which is a difference of 2 binomial coefficients. And of course, that's going to go back to what I did in the first third. What do we do? Well, what are we doing with these rectangles? We're loading coefficients into them. So that's going to be a weak composition of your L with two end parts. But we got shifting, so we're going to have to throw away anything where I put positive entries in the bottom. Like we want to make sure there's a 0 there. And so if we do the counting, that's just going to be okay, the weak composition of L with two end parts is the first binomial coefficient from the weak composition count that I talked about early on. And then if I want to throw away the things with all ones in the bottom, well, just pre-assign every box with a 1, subtract L off of that, or subtract N off of L, and then that'll give you the count that you're not going to use. Now, with the binomial series, I could rewrite this is a generating function. You can see in the first one, if you cover up the x to the n, that's got the right index because the way I indexed it was with a +1, so we should have 1 less there. And then you can wash out the 1 minus x to get this second form. All right, so that's a generating function. Now, in general, okay, so what can we do with that might be interesting, or might be something that undergrads can take a look at anti-magic squares and boot that up to something new. So a conjoined composition, what are we going to need? I want a rectangle, so I got to give it a type of how big's the rectangle. We're going to load it numbers into it, so it'll still be a weak composition. So we'll have an L, and then the number of parts is just the number of boxes in your rectangle. And then we want this relation where I could just move ones from one row to the other. So I just want to have a lot more rows to deal with, but they're moving very uniformly so that we'll get something nice out of this. And then for 3, 4, that's what the shift relation looks like. You can imagine what it is in general. All right. So that definition, not so great because I'm taking something that we know like compositions and taking a quotient. Nobody likes quotients. So if you want something that's free, meaning it's going to have those relations, but I'm not going to have to impose anything on it, what you can do, say I want to do 2, 3. What I'll do is I'll take 2 times 3 sextuplets. I'm going to put the first one, the M1s at the front, and then we're just going to cycle that across till I have these, they stop being adjacent when it loops over. That's going to have exactly the relations that we want. If I take the sum of the top row, that gives me all ones. Sum of the bottom row gives me all ones, and then you can check that that's the only relation that you can have. Type 3, 2, same idea. They fit together nicely. We take the sum in pairs, you're just going to get all ones. And then if you want to do this in general, you're just going to take, say for Mn, take an Mn by n by n square, and then just put m diagonals in, and then just chop out and take all the rows. And then that's going to give you that shift relation that you want with the right indices. Takes a little bit of work to stare at that and see what's going on. But that's what you do. And typically we haven't done much with this. This is just sort of we noticed it working on the generating function more than this. Okay, so big result so far. We're going to keep working on this during the summer. If I want to count by weight, let's call it weight or line sum or index. If we're putting L balls into our composition, if I've got an m by n rectangle with the shift relation, then this is going to be the generating function that comes out. So when I have m equal to 2, we recover the counting function for anti-magic squares. And where does this come from? It's kind of the same idea as I did for counting anti-magic squares. We load things into the rectangle. We'll go by induction. You'll have an m by n rectangle, and all you're going to do is attach a weak composition to the bottom that has to have a 0 in it. So that way we keep the upshifted property. And then you just count, and that's going to give you the factor that you want for the bottom row. And then, like before, we're making independent choices, so we just multiply the generating functions together. And then that gives us the induction step. And then you can just boot that up to a complete formula. So we got a generating function now. All right, so we kind of, like I said, leave the anti-magic squares and conjoined compositions behind, other than counting them. So what can I do? Well, the next step will be, want to go back to the binomial coefficient thing and take a look at what happens when we break out all the factors and see where if things go to something that looks nice. So with Stanley's formula. So we take this. We got the generating function. What things can we expect from this? So this is more spoilers for Stanley stuff. When I wash out the 1 minus x term, remember from the binomial series, the binomial coefficient I'll get from the bottom with the largest index, we take a 1 off of. So that's going to give us a 2n minus 2 for the polynomial. The factorization is going to give us the zeros. So if you factor both of those, we'll have those zeros in common. And then also, if we sub in the minus L, like I mentioned before, we're going to get no sign out in front, and it's just a shift by n. All right, so the reciprocity formula says, okay, we're going to be even in every case now, and then there's a nice shift, even about certain axes. So of course, take a look at the polynomials, because seeing is believing, and there you go. Interesting to note, so I didn't give you the numbers, it's 3, 4, 5, and 6. The 4s always have that double zero. So they always have touch the axis and have the critical point there too. All right, so so for Stanley's formula, the polynomial that comes out is going to have 3 parts. We're going to have a factorial part. We have the part for the zeros, which will be this, like, this arithmetic progression of differences of 2 squares. And then we're going to have this final term, which, as nice as you're going to get, is you can come up with a nice formula for the coefficients in terms of elementary symmetric functions, which you can almost anyway when you multiply a bunch of factors together. But you'll note we're only going to keep they only skip in 2s. All right, so where does this come from? Oh, okay, so for an example, let's take a look at what's going on with 4. So that's the explicit polynomial for 4. The elementary symmetric functions give us this. And then, as noted, we get the double zero at the -2. All right, so it's worth just going through this one to see what's going on here. There's something interesting going on. So the idea will be, I should have put the formula up again. The 2 binomial coefficients here for the 4, I could factor out this one from each of those. And the idea is going to be, well, I want to write everything in terms of L plus 2. So the other factors, we'll notice one goes down, one goes up. And for any of these functions, they're all going to have that feature where it's going to be perfectly balanced around your axis symmetry. For the elementary symmetric function part, I'm going to swap out an L plus 2 for an x so it's easier to look at. And then you notice these polynomials are the same up to the sign in the second one. So when I take the difference, we're going to wash out half the terms. And then you see where the elementary symmetric functions are coming from these polynomials. And like the other interesting thing is the double zero. I'm getting a double zero because there's an extra factor of x here. So that kind of magically comes out of this horrible part into the nice part. All right. How about in general for Mn? So that was anti-magic squares. Same reasoning. We can get the polynomial explicit, the degree explicitly, the zeros explicitly. Reciprocity is going to depend on your parameters. And then we also have this factor to let us inductively calculate counting functions as m increase. So nothing for n, just for n. Okay. How we doing? Good. So of course with undergrads, we want to put them into the explicit stuff. So if I do n equal to 2, I forgot to put the boxes up here. So anti-magic squares, remember, it's 2 rows and it gets long. So if I let n be equal to 2, I have 2 columns and we want to let m go long. So this is kind of like the opposite case for anti-magic squares, or the transpose, I guess. you call it. So here with the formula, what happens? We can factor out a lot of 1 minus x's, and so we get a nicer generating function, which is almost a generating function for counting points in cross pilotopes. It's off by like a 1. What do we get for our stats? We got polynomial degree n, a single 0. Reciprocity is going to change depending on whether we're odd or even. And then the function I use to increment up, so it's not going to be partial sums anymore, but if you expand that, it's almost twice partial sums. So if I take 1 plus x over 1 minus x, that's going to give you use the first term as is, but then double all the others and add. That's going to give you the hockey stick rule. All right, and then of course we want to see how good we can get with trying to write down a general formula. Right now, this is as good as it's going to get, and we'll try to drill down over the summer, but I'm not hopeful for this one. What do? You're just going to, if you have index n, we take 1 off. You're going to take that row of Pascal's triangle and then load that up in front of the series that come in from, or the terms that come in from the binomial series, and then they're going to decrease by 1 as you go along the top. And then you can see the even and odd is promised. So that's really, or here, yeah, it goes even and odd. So that's as explicit as, well, we want to get. So these two we can write out, but for now, we're keeping that.
What's the relationship between the rows and the F's?
So, generating function. So I've got a sequence. The sequence is the rows. So if I have row of L, I'm going to attach an X to the L to that. That's going to give us the generating function, which is the F.
F is counting the composition things, right?
No, so F isn't counting anything. F is arranging all the counts into a power series. Yeah. So, right, there's a lot of, so the thing that really messes me up trying to keep this clear is, so I got an X and I got an L to keep them separate, and I should have used X earlier now that I think of it. For a sub, right? It's a problem because the counting function itself is a polynomial, which will make you want to use X when I'm going to use L instead. So the generating function's X, counting function is L. So we're up. That's why we're up. So counting function is rho, which picks up an L for line sum. The generating function, which I don't. Where's the last generating function I had there? If you expand that out as just a power series, the coefficients are going to be the rows at some L with X to the L right next to it. Yeah. Okay. Right. So let's take a look at the table. Now the hockey stick rule is the thing I want to do first, like we did before. The way I set this up. Our 0 column is not going to be just the 1 now. It's going to be a 1 over 1 minus x squared. If you take a look at the generating function, if you put 0 in. So I'm not going to get a 1 in there by itself. It's going to be alternating between 0s and 1s. The hockey stick rule, what's it going to do? Say I have the 44. I take a look to the left. We got a 16. Then I'm going to add twice the values that are above it. So not quite a partial sum, not quite twice a partial sum, but something we can work with. And we get lucky in this case in that, well, if I look at the 19 above the 44, it won't take away everything above the 16. It'll take away everything but 1, 9. So what you get instead is, this is good. It's not a 3-term relation like Pascal's identity. It's a 4-term. So that gets me, that like frees me away from the top row, and I could use that 4-term anywhere I want in the grid. Where there, you've always got to go back to the top. So if you want to do polynomial things, you got a relation there too. Let's see what else we have here. Still have Vandermonde convolution. For Vandermonde convolution, before we had a single binomial coefficient as the answer. Now that's not going to be quite so nice because wherever you put your rectangle, you're going to pick up 1s in this column, which are going to be the number of terms in the nicest form it can be in. Same idea, same explanation as before. What we do, I pick your favorite rectangle, flip, dot product, and that won't change as you telescope in or out. But the final good formula would be what you get when you dot with column 0. All right. Okay, almost out. If we do n equals 3, so we can still get some stuff, but of course the resolution on this starts breaking down. What happens is in the numerator, you wash out the negative ones. You've got a 3-term polynomial that you're going to take to a power, so not so good. The stats, degree 2m, we now have 2 zeros for each of these. Reciprocity is always going to be even now. These are always going to be even polynomials. And then we got a choice of how we want to increment up. And to get something done in 2 minutes, it's better to increment up with the first one, just because the binomial theorem we still have available, whereas with the 3-term part, you got to do some trinomial theorem, which is a little bit grittier. So the difference in the formula from before, we're still loading in the row below from Pascal's triangle, the row above. We now have to use alternating signs, and then the increment or decrement is a 3 as you go down. Only going to do one example with the m equal to 3 here, but you can see that's even. And then for our hockey stick rule, when you sort this out, it's still not bad. It's hard to control, but it's not something that's alien. It's just going to be a 1, and then you follow it with arithmetic sequence with 3, with difference 3. So when I go to the table, same idea. I'm going to use 1 over 1 minus x cubed in column 0. For the hockey stick rule, what we do is the 163, we take the 1 next to it, but then I've got to wait as I go up the column for the result. And then that lets me generate everything to the right, and you can also go to the left also. If you want Pascal's identity, again here, this is one I feel like we got really lucky with, just staring at it. What you'll do is the 163, I take a look to the left and add the 3 up. We want twice the 45, which is right above it, and then you subtract the 9. And so it's a 6-term relation, which, like I said, it's good as it's going to get. I feel like if we were to go to 4, we're not going to find it. But who knows? So that's Pascal's identity. And then finally, we have Vandermonde convolution again, and it's the same explanation. Doesn't really depend on, so I mean, the Vandermonde convolution will work for any m and n if you can get the table set up. And then that's talk. And so for references, these are all the books I've been looking at for this, which isn't like the articles, but all my thinking's coming out of things here. So that's my talk. So thanks. That's the fun.
Any questions in person?
So in the rows, that if you have the same like n, I see the 3, 3, right?
So
I see the terms.
So where do we want to go?
The 4 slides back.
Stay
Right
with
there.
Okay.
Rows of 3, 3
Right.
of L. It looks messy. I was thinking if you have rows of n, it should have been simpler.
I don't know.
It's messy.
Oh, I haven't tried. It's like I said, some of this
It's
is
the
progress.
working.
Yeah.
Thanks.
Other questions in person? How about on Zoom?
I don't see anything.
Anyone? Okay. Well, no more questions. Let's thank the speaker again. Thanks. All right. Thanks for coming, everybody. We've got another talk in 2 weeks. So see ya.
Thank you.